3.4 Zeros of polynomial functions preparation. Okay, so we're looking at different kinds of symmetry. So we have Y symmetry, which you can see right here. We have a Y, this vertical line, and you can see that it's symmetrical, or there's kind of a mirror image on the left and the right of this. Over here, we see this is X-axis symmetry, and you can see that on the top and the bottom, it's almost like there's a reflection up here and down here. And then you have origin symmetry, which you can see vertically. We have reflection across the origin, so you can kind of see how this would be a reflection, but more like twice, like 90 degrees and then 90 degrees. 90 degrees to the right, and then 90 degrees up, or vice versa. Now, you can see right here, this is a graphic illustration of y-axis symmetry, where you can see if you have a negative x, okay, and a positive x, they both spit out the same positive y. So the test, the algebraic test that we're going to have is, we're going to plug in a negative x, and we're going to see if we get exactly the same y. Okay, and that'll make more sense when I give you an example. The next one, for x-axis symmetry, we're going to see that for a negative y and a positive y, you can see that it's going to spit out the same x. So it's basically the same as the other one, but in reverse. And for the origin one, to test for that, you can see if you have a negative x and a negative y, we're going to spit out the same equation. Okay, so, and they're described right here, the different definitions of symmetry right here, and what you plug in, and then how you test it, right? So here's the definition of, first we have y-axis symmetry. It says substitute negative x for x in the equation that results in an equivalent equation. Then we have symmetric with respect to the x-axis. What we do is we substitute a negative y in for y in the equation, and it results in an equivalent equation. And then finally, symmetric with respect to the origin. What we have is substitute negative x for x and negative y for y, and the equation results in an equivalent equation. All right, so let's try a couple of examples of this. Okay, now first of all, just looking at this, we can tell that this is actually going to have x-axis symmetry, because you can see right there, it's going to flip up and down, that it's a mirror image across the x-axis, okay? So the top and the bottom are mirror images of each other. So what we're going to do is we're going to algebraically verify this. Okay, so let's see. Let's say we want to do y-axis symmetry. Okay, so how would we do that? What we would do is we would plug, first I'll write the original equation down. So it's x is equal to y squared minus 1. And to find y-axis symmetry, we plug in a negative x, right? So negative x is equal to y squared minus 1. And as you can see, these are not equivalent, okay? Whether I solve for, I can even divide everything by a negative 1 or multiply everything by a negative 1, we just flip the signs, and I still can't get the original equation. So the point being is, when I plug in that negative x, even if I do a little bit of manipulation, I can't get it back to the original there. Okay? So what we would say as far as y-axis symmetry, it does not have it. No bueno, right? All right, so let's try the next one. Okay, so we're going back to the original one. And now instead of plugging in, well, let me write this up. First, we're looking at x-axis symmetry. All right, so what we do here is we plug in, so you plug it basically opposite, right? So when I'm doing y-axis symmetry, I plug in a negative x. When I'm doing x-axis symmetry, I plug in a negative y. Okay, so we kind of plug in the opposite. Okay, so I'm rewriting the original equation, but wherever I have a y, I'm going to plug in instead a negative y. Now, when I square a negative y, I get back y squared, because a negative times a negative is a positive, and we keep the negative 1. And the question is, did I get back the original equation? And the question on this one, we see, yes, we did get back the original equation. So this actually has x-axis symmetry. Okay, now we can already tell here that this does not have origin symmetry. There's no vertical reflection, right? That's going to make this original one. So, but we can verify that algebraically. So let's verify that algebraically a little bit, okay? All right, so we're doing origin symmetry. So I'll write down origin symmetry first. Origin symmetry. We want to memorize the test, right? So origin symmetry, we're going to take the original equation, but wherever we had the x and the y, I'm putting in parentheses where I'm substituting, we are going to plug in the negative version, right? And if after we do simplification, we want to see if we get back the original one. Now, negative y times negative y, or negative y squared, which is negative y times negative y, that gives you positive y squared. Now, as you see, I did not get back the original, okay? Now, since I'm not going to be able to get back the original, we would say this does not have origin symmetry, which just confirms what we could already see there. So it did not have y-axis symmetry, it did have x-axis symmetry, it did not have origin symmetry. Okay, so let's try another one. So we are going to determine whether the graph of y is equal to x squared minus 1 is symmetrical with respect to the y-axis, the x-axis, or the origin. Okay, so I'm going to go through all the tests. Now, again, you can just look at here, and we know this is, for instance, the y-axis, right? And you can see from left to right that this would be symmetric with regard to this y-axis here in the middle. Okay, so we already know that it has y-axis symmetry. You could look up and down. Does it reflect up and down, right? And the answer to that is no. And since that's the x-axis, we would say it does not have x-axis symmetry. And we could look whether it reflects vertically. No, it does not. So it does not have origin symmetry. Now what we're going to do is we're going to algebraically test them, and then we're going to verify what we can already see. Okay, so let's try this. So let's say I want to do y-axis symmetry. And if I want to do y-axis symmetry, right, y-axis symmetry, what we are going to do is I'm going to take the original one, but wherever I have the x, instead I'm going to plug in a negative x, right? And negative x times negative x is positive x, so we're end up with x squared minus 1. And as you can see, right, I was able to get back the original equation. So check. We actually were able to obtain y-axis symmetry with that test. Okay, so let's look at the x-axis symmetry. X-axis symmetry. Okay, x-axis symmetry. So what we're going to do is we're going to take, I'm going to rewrite the original. I probably should do that in the other ones, but that's the original equation is y is equal to x squared minus 1. And we are going to plug in a negative y. Okay, now as you can see, I didn't get back the original equation. The right side matches, but the left doesn't. And there's no algebraic manipulation that I can do to this one to make it match. So for instance, I multiply or divide everything by a negative 1. I'd flip the signs. This would just turn into y is equal to a negative x squared plus 1. So neither one of these matches the original. It doesn't matter. I can make the left match, I can make the right match, but I can't make the right and the left match. So this does not have x-axis symmetry. So let's try origin symmetry. Origin symmetry. Okay, so what I'm going to do is I have the original equation, which is y is equal to x squared minus 1. And what I'm going to do is I'm going to plug in a negative. I'll put parentheses where I'm plugging it in. I'm a little inconsistent with that. Okay, so what that gives me is negative y is equal to negative x times negative x is positive x squared, right? So x squared minus 1. And as you can see, we did not get back the original. This right here and this right here, right? They do not match. And since they do not match, they do not have origin symmetry. And there's nothing we can do to make them have it. Again, I can multiply everything by negative 1, and then I could get positive y is equal to, but then the right's going to have the opposite sign. So there's nothing I can do, no simple algebraic manipulation that's going to cause that to be equivalent to the original equation.